Only 8 students so far. Should I wait for some time or? And 10. It's less than 50% yet, but we'll start anyway. Uh, the slideshow. Good afternoon, everybody. We actually will continue from the discussion of oblique shocks. In fact, what we are doing now are twofold. One is reviewing shocks and expansions, which we are going to do soon, and simultaneously looking at what is meant by the hypersonic limit for each of the important parameters, like what we have done already for pressure ratio, density ratio, etc. So last class we have seen that as m tends to infinity, we can get some handy relations which give us some trend. Now we just take it as the trend actually, because there's nothing like infinity. So what happens when m increases? What happens to these ratios, and what's the trend that we can observe from them? That's importance of looking at this hypersonic, so-called hypersonic limit. So we continue from density ratio, which we have already seen. We see that the oblique shock relation rho 2 by 4 rho 2 by rho 1 that transform to just a relation between gamma plus ratio between gamma plus 1 and gamma minus 1, which means that the ratio of density across the shock becomes practically or tend to become independent of Mach number as Mach number increases. Okay, now coming to this all important the theta beta m relation, which we reviewed in the previous class. As we know, it relates the flow deflection angle theta, the Mach wave, the shock wave angle beta, and the upstream Mach number m, or m1 here as it is shown. And so when the basic relation we have just recalled that in the previous class. Now, if you look into that, we can see that when m1 increases or m1 tends to infinity, the first term. Look at the first term. We are going to progressively look at lower values of theta, which means that is hypersonic flow and lower values of theta. Why is it? Because many of the hypersonic applications will pertain to sharp edge comms. In fact, not all of them, but many of them. In fact, we should be careful. Actually, there is a category of hypersonic applications where you will have blunt edge. But as far as sharp edges are concerned, we know that when theta is less, beta also tends to be less. So when theta comes down, beta also comes down. So there are two things happening when we look at the theta beta m relationship. M tends to infinity, and the hypersonic Mach number, hypersonic limit, we consider m to be tending to infinity. M increases, the m1 actually, the upstream Mach number. And as long as we are focusing on small deflection angles, we can also say that beta tends to 0. That is, when theta tends to 0, or when theta reduces, beta also reduces. I guess we have reviewed that from the theta beta graph last class. So Now let's look at the relation again. So tan theta, as theta tends to 0, tan theta tends to be theta. And similarly, sine beta tends to be beta. So sine squared beta becomes beta squared. So the numerator becomes m1 squared beta squared minus 1 divided by the denominator becomes m1 squared gamma plus 1. Why 1? Because cos 2 beta. As beta tends to 0, cos beta tends to 0. So does cos beta tends to 1. So does cos 2 beta. So it just becomes gamma plus 1, the multiplicand. That plus 2. Now, if you focus further into this relation, m1 squared beta squared, when we consider that as a high number because of the magnitude of m1, m1 can be neglected, right? So the numerator can be taken as m1 squared beta squared. Similarly, in the denominator, 2 can be neglected because m1 squared is a large quantity. So if you ignore these two, this gets further simplified as 2 by beta into m1 squared beta squared divided by m1 squared gamma plus 1, which can be further simplified as gamma plus 1 by 2. Beta gets cancelled, etc. So when we m1 squared gets cancelled, etc. Beta. So beta by theta can be written as gamma plus 1 by 2. What does it mean? It says that when the hypersonic Mach number, as Mach number increases and as the compression angle reduces, which means that when we are considering hypersonic flow past thin bodies, the ratio of wave angle to the deflection angle, beta by theta, the ratio of shock wave angle to the deflection angle is independent of Mach number, and it tends to be gamma plus 1 by 2. So it only depends on the gas property gamma. So beta by theta tends to become gamma plus 1 by 2 as as m1 increases, and simultaneously when m1 increases and theta reduces. So this is an observation that we can carry forward. We'll have some applications for this as we go by. So this is one. This is a simplified form for the otherwise complex beta tan theta or beta relation for theta beta. Now, okay. Before going further, I'll pause for a minute. If you have questions or anything to be clarified from what we have discussed so far, you may please raise those. Okay, then we'll proceed if no questions. Now we will also quickly look at the expansion wave, the isentropic phenomena, which we call as Prandtl-Meyer expansion. So please remember that when flow expands around a corner in a process which can be approximated as adiabatic and reversible, adiabatic and reversible, that is isentropic. The phenomena is called as Prandtl-Meyer expansion, an isentropic process, and it's typically it happens when supersonic flow encounters what we call as a convex corner. A convex corner, that's a corner where the flow expands, that is a corner like this. That's what we call as a convex corner. Remember that what we call the compression corner as a concave corner. So what we are now talking about is a convex corner. So when you have supersonic flow over an expansion corner, like the ones that are shown here, we can expect a series of expansion waves. I mean, it could be either a smooth expansion or an abrupt expansion. In either way, in both the cases, you can assume it to be happening over a series of expansion waves. So basically, they can be approximated as a series of subsequent Mach waves. So infinitesimally small pressure waves or through which the expansion happens. So unlike oblique shock, this does not entail increase in entropy. This is a gradual process. It's an expansion process. And this is what we call as Prandtl-Meyer expansion. And please remember that for Prandtl-Meyer expansion, we have derived some relations similar to a compression case also. That is the application of governing equations were made by considering it as a continuous process. So instead of having a pressure jump across a control volume, what we have considered in this case is differential expansion process, because it's a continuous process. In shocks, we consider a control volume and abrupt change across it, whereas this is a continuous process. So we can assume a differential process, which is continuous all through. So based on this, we identify two Mach lines, the forward Mach line where the expansion just starts, and the rearward Mach line where the expansion completes and the flow becomes parallel to the new surface. So to begin with the flow, we are assuming anyway in viscid flow. So to begin with, the flow is parallel like this. After the expansion, the flow is parallel to the new surface. So that those are the two limiting Mach lines that we consider. So and the expansion we are considering it's happening over an angle theta. So based on this formulation, we could relate all this through a small geometric construction as well as the application of the continuity and momentum equation. We have derived an expression for what we call as the Prandtl-Meyer function, nu m. Nu m, the Prandtl-Meyer function, where a function of Mach number, that is gamma plus 1 divided by gamma minus 1 tan inverse root of gamma minus 1 by gamma plus 1 within the square root itself, root of m squared minus 1 minus tan inverse square root of m squared minus 1. So this is the expansion, the Prandtl-Meyer function, which we know is available in the form of tables, which we have made use of for calculating the consequences of the expansion. That is either to calculate what is going to be the downstream Mach number, or to calculate what is for a given Mach number what is going to be the theta. So based on the construction that we have on the left side, that is this, we can relate that theta 2, that is the new direction of the flow, can be related as the difference between the Mach functions for the leading Mach number and the trailing Mach number. The leading Mach number, that is the upstream Mach number, and the downstream Mach number. So if you calculate the Prandtl-Meyer function for the downstream Mach number and subtract it from the upstream Mach number, you will get the difference in the two, which is basically the expansion for the flow, or rather the angle through which the flow turns during the expansion process. So this is what we called as Prandtl-Meyer expansion, and we know that it's an acceleration process. So across it, the Mach number increases, and because it's an expansion, static pressure drops. Stagnation pressure, we assume it to be constant because it's an isentropic process, and stagnation temperature also remains constant because it's an adiabatic process. So static pressure being static pressure reduces as opposed to the increase in oblique shock. In across oblique shock, static pressure increases. In expansion fan, static pressure drops. Stagnation pressure drops in the case of oblique shocks, but stagnation pressure remains constant across an isentropic PM expansion fan. So these are some of the characteristic differences between the oblique shock and the expansion fan. Now, the application, or we can make use of the expansion fan to, or the concept that we have considered now to study the flows like this. Say you have the leading edge of a sharp object here, where on one side, and it's at an angle. It's an at an angle, that is with an angle of attack with the upstream flow. So you have the flow, the body is pointed at an angle of attack. So which means that on one side, you will see a compression corner. That is the the lower side of the body acts as a compression corner. The upper side of the body acts like a expansion corner, right? So to solve this upper side, you can use Prandtl-Meyer expansion theory. Whereas the downstream side, you have to model using oblique shock. So this is the occurrence when you have an angle of when you have a pointed body at an angle of attack exposed to supersonic flow or hypersonic flow, either. Okay, so that's a quick review of Prandtl-Meyer expansion fan. And the application of Prandtl-Meyer expansion are many in real supersonic flow situations, like in the intake of a scramjet, and to some extent a ramjet also. You will have series of oblique shocks and expansion fans. The intake geometry itself will be in such a way that you will have few oblique shocks and you will have subsequent expansion fans also. So some of them are marked in this. I will try to highlight it. So you have an expansion wave that is marked here, starting like this, that is and near the corner. So such expansion waves can be solved to some extent by making use of the Prandtl-Meyer expansion analysis. Okay, now so that was a quick review of how Prandtl-Meyer expansion is formulated. Now let's again go through the hypersonic limit. That is what happens for the Prandtl-Meyer function when Mach number increases. Okay, by the way, any questions so far about the review of Prandtl-Meyer expansion? Four plus 1, 2, 3, 4. 4 plus 3, 7. 7, 8 or so. Why the attendance is so low today? Any guess? Anything special today or? No response. I do. I believe that is. I mean, I'll have to go back to the attendances. I don't know whether it used to be always so low, but today I noticed that it's quite low. I guess even 50% of the class has not turned up. 9, yeah, 9 only. I think. Again, so if no questions, we'll proceed. So the hypersonic limit. Now let's see what happens when Mach number increases. Again, look at the terms that we have here. The Prandtl-Meyer expansion term, which has a square root of m squared minus 1. I'll just go back a couple of slides. Yeah, you have a square root of you d theta is square root of m squared minus 1 dv by v, and the Prandtl-Meyer expansion function itself has a square root of m squared minus 1. Actually, two places where m squared minus 1 is appearing. One is on the in the first term inside the square root, and in the second term as tan inverse square root of m squared minus 1. So the first thing that we observe is that square in m squared minus 1, as m squared increase, or rather m tends to infinity, m squared is much higher. So the term 1 minus 1 can be neglected, which means that square root of m squared minus 1 can be approximated as square root of m squared, which is m itself. So this term can be the square root of m squared minus 1 in the two terms can be just taken as m. Now, when you substitute it back here, the expression becomes gamma of m. Gamma is equal to gamma. Nu of m is equal to gamma square root of gamma plus 1 by gamma minus 1 multiplied by tan inverse gamma minus 1 by gamma plus 1 multiplied by m minus tan inverse m. Tan inverse m, instead of square root of m squared minus 1, it just becomes tan inverse m. Now, tan inverse m can be written as pi by 2 minus tan inverse 1 by x. You would have done this derivation in your +1 +2 trigonometry, I guess. Tan inverse 1 that is one of the fundamental derivations when you study the inverse of functions. Tan inverse x is equal to pi by 2 minus tan inverse 1 by x. And in case if you don't remember, I just kept a in fact, I felt so lazy to do that the whole thing again, so I just got it from somebody has done it on the in YouTube. So I just taken the screenshot. It's a very simple derivation actually when you consider a right angle triangle with sides x and 1 and the angles theta and phi. You can easily show that tan inverse x plus tan inverse tan inverse x plus tan inverse 1 by x is equal to pi by 2. So which actually gives this relation tan inverse x is equal to pi by 2 minus tan inverse 1 by x. If required, you can just see that this one. Anyway, I just put the final derivation here, though it's a video. I just took the last screen of it so that if required, you can refer to it. But I'm sure you will be remembering that. Yeah. Anyway, so that expression that comes to be tan inverse x is equal to pi by 2 minus tan inverse 1 by x. So that we can use handily, that can be used conveniently in this particular relation. In fact, talking about that video, that the person who does that derivation must be a mathematics professor also. He at the end of it he says, so he says it's a simple a simple proof, etc. He does that. He scribbles down the whole solution, a whole proof, and close to then he says that this is the relation, but he also remarks that I have not seen this being used anywhere, so it may not be of much use, etc. So whereas we know, or we are readily seeing a use for that particular relation. So mathematical relations, though mathematics professors may not be seeing their utility, we engineers will say you make use of them somewhere or the other. So is just one such example where probably the application is not obvious to mathematicians, but we have a specific system where situation where we use that particular relation to simplify this further. Anyway, that's okay. Then so this tan inverse x again can be expressed as a series 1 by x minus 1 by 3x cubed, etc., etc. And as usual, we'll neglect all the higher order terms because x here is Mach number, right? Pi by 2 minus tan inverse. So we have tan inverse m here, so that this the first both the terms have m, and so that this x here will have a term containing m. So at higher Mach number, we are talking about m tending to infinity, which means that 1 by 3x cubed and 1 by 5x to the 5 etc. can be easily neglected because m is too high, which means that we'll be just restricted to tan inverse, or we will be approximating the whole thing as one tan inverse 1 by x is equal to equal to 1 by x. So making use of this expression and this the subsequent two simplifications, it can be written as, or the whole Prandtl-Meyer expression. I just written the intermediate step here, which eventually leads to theta being equal to nu of m2 minus nu of m1, which can be written as finally as 2 by gamma minus 1 minus 1 by m1 minus 1 by m2, which is a fairly straightforward relation, particularly as compared to how it used to look like in the beginning. So as Mach number tends to infinity, the deflection angle, the flow deflection angle theta, can be written as 2 by gamma minus 1 minus 1 by m1 minus 1 by m2. Now, similarly, all the other relations like P2 by P1, we have an expression for Prandtl-Meyer expansion for the P2 by P1, which is straightforward because P naught remains constant. So if you just apply that, P2 by P1 can come readily from that. So P2 by P1, that simplifies to, so the expression on the top, when Mach number tends to infinity, this simplifies to, keep in mind that is an expansion process. So M1 tends to infinity, M2 also tends to infinity because M2 is anyway going to be higher than in M1. It's an acceleration. So when you substitute that here, we can show that P2 by P1 becomes M1 by M2 to the of 2 gamma by gamma minus 1. That is static pressure ratio across the expansion fan as m tends to infinity, m tends to be very high, tend to be m1 by m2 to the power of 2 gamma by gamma minus 1. Today we will just close this by looking at this pressure coefficient definition also, which we are going to use subsequently in many of the oncoming sessions. CP, the pressure coefficient, is very convenient way of for expressing the pressure distribution, static pressure distribution, and starting from thermodynamics or even fluid mechanics. Actually, starting from fluid mechanics itself, you have used CP, the pressure coefficient, like in many of the flow related or aerodynamics, drag related pressure distribution estimation, etc., where you have considered CP for different shapes, different bodies, different flow conditions, etc. One way to express that is CP is like a pressure difference term divided by Q1, where Q1 is the velocity, the term containing velocity squared. So one way to write that is as Q1 is equal to half of rho 1 V1 squared. So CP can usually be written as P2 minus P1. That is basically like a pressure differential divided by half rho 1 V1 squared. The importance of it is it gives you a non-dimensional parameter. It gives you a non-dimensional parameter which relates the pressure differential to the velocity and the fluid property density. So it's a convenient parameter, pressure coefficient in aerodynamics. Pressure coefficient is most commonly used for expressing the pressure distribution across bodies, particularly for external aerodynamic applications. Now, we will make use of pressure coefficient, but then since we are talking about supersonic or hypersonic, actually we are talking about hypersonic flows. So even for supersonic flows, a better way of expressing this or more suitable form of expressing this will be, instead of using P1, rho 1 and V1, we will express that in terms of Mach number. So the steps here are quite straightforward. I'm just writing Q1 is equal to half of rho 1 V1 squared, which is actually equal to half of rho 1 V1 squared into, you just multiply both sides by gamma P1, numerator and denominator, or you multiply by gamma P1, divide by gamma P1, and then rewrite the whole grouping as gamma P1 by 2 multiplied by A1, V1 squared by A1 squared. This A1 squared comes because you have a P1 here. Sorry, gamma P1 here, and P equals rho RT. So this can be written as rho RT, right? So that which can be, and we have gamma already here. So we can relate that to A1 squared because we know that A1 is square root of gamma RT. So the reason that we transform it like this is because we can now write that in terms of V1 squared by A1 squared, which is nothing but Mach number square. Okay, V1 by A1 is M1. So this gives us Q1 is equal to gamma by 2 P1 M1 square, which eventually gives CP is equal to P2 minus P1 divided by Q1, which is equal to 2 by gamma M1 square P2 by P1. So please note that we continue to use the sorry. We continue to use the CP definition, but now we are going to use that in terms of Mach number instead of velocity. So CP is defined in the same way as you have used in aerodynamics, P2 minus P1 by Q1. But instead of velocity, we are going to write that in terms of Mach number because we are going to use Mach number more commonly in hypersonic flows to characterize the flow field than velocity. So what is going to characterize the flow field is Mach number. So we have CP now written in terms of Mach number. So whenever we need CP, we will recall it as 2 by gamma M1 squared multiplied by P2 by P1 minus 1. So this will be quite handy, and we'll be referring back to this relation quite often going forward. I guess I'll stop here for the day. What we are going to do next is, now we have sort of reviewed the fundamental aspects related to pressures and expansion, pressure waves and expansion waves. Now we will see how some of these can be used in hypersonic flows to calculate the hypersonic aerodynamic forces. So when we are going to look at it, we will be looking at the specific theoretical formulations for pressure distribution over hypersonic bodies and the calculation of aerodynamic forces, etc. And we will be using different approaches, different theoretical formulations, and we will see what and where are they applicable to, where they are applicable in under what situation. So that is going to be the focus for next several sessions, where we are going to always focus on inviscid flow application. So that's sort of goes without saying that the next few sessions are going to be focused on inviscid flow. We will later in the course, we will address the effects of viscosity. Okay, let's stop here. Just since if any, you can please raise. And next class, we will have some, again, I'm formulating some tasks which I'll assign to different groups in the next class, mostly in the next class. So I hope I'll be able to line them out. I'll be able to plan that before the next class. I guess we have an hour tomorrow also. So anyway, I'll line that up and I'll explain what each team has to do when I present it. So that will involve the application of some of the concepts that we have discussed already. So I want you to do that USS and present it so that you apply your wisdom to it, so that that you will be able to readily recall it and apply it. Again, questions, please. No questions. If you don't have questions, we can stop here for today.
Okay.
Okay then. Thank you. Thanks. Bye.
Thank you, sir.
Thanks. Thank you.
Thank you.